Anybody heard from Lynn?
Yes, Lynn will be with us, should be with us today. I talked to him yesterday. He is finishing up some stuff. 224 buck boost transformers. What do y'all know about them? You ever heard of them before?
Ever?
It's kind of a weird term. So it's pretty, it'll make a lot more sense in just a second. I'll put it on the board. Let me put this down. I didn't kill myself. All right, there we go. All right, so basically they mean that, I don't know if you can see it as good, but it is, buck means negative or subtractive, and boost means positive or additive. And that's kind of what we'll get into today with that. All right, hopefully the rest of them will jump on here in a few minutes. If not, we have it recorded so they can keep along with us. All right, so if you'll follow along in your hymnals, we're on the first page, 224, okay? And we are looking at additive polarity. I'm going to give y'all a book as well here. We'll come back to them. Let me get the book here. It's got a fancy little deal where I can actually pull this up and see it. I like that. So let's share that. You guys, all y'all probably have your book, but there you go, just in case you don't. All right. It even turns the pages. Isn't that cool? We'll zoom in down here on the additive polarity thing. All right. So what's the point of this extra transformer, and why would you even need it? So sometimes if you need 240 or you need more than that, you can add this extra transformer, just like the little small one I have. You can add one more, and you see how they have tagged them together, H1 to X2, H2 to X1, and you look and you'll notice that it has 264 volts of the additive measurement. That is 240 on the first one from the primary, and you got 24 more induced from this one, and you can use that as an additive amount of voltage. Why would you do that? What would be the point to have something like that? So this voltage is induced in the secondary winding, and the terminal at X1 is positive 24 volts if measured at the same point, and the sum of the voltage across the higher voltage winding and lower voltage winding. If the voltage of the higher voltage waveform were added to the voltage of the lower voltage, the additive result will be 264 volts. You can see here the normal 240, but if we add it, our waveform gets a little bigger. We get that added boost, and that's what they call that, a boost of 24 volts. In the same respect, if we got a situation where we need less, so a lot of times you'll use a 32 volt buck transformer. Anybody know why we would do that? If it's 240 primary, but we would want to add a 32 buck transformer, maybe under some three-phase stuff. What do we use? What is sometimes they use in three-phase? What voltage? It's kind of common.
Come on, 480.
277. 208.
Right. So, and what I meant by, and I wasn't very clear with that. Let me be a little more clear with it. 32 buck, or a subtractive number, 32 from 240 would be 208. We're going to get into that in just a second. Or in this case, 240 with a 24 volt buck transformer would be 216 volts. Let's go back to this. Yeah, we still don't have. So that'll be back it back out. So what's all the big deal about the polarity? Well, these are little small capacitor transformers, and most of them, and they're wound for additive polarity. They're connected either boost or they're buck for decrease. Sometimes you want to boost the input voltage. Sometimes you want to buck the input voltage and make it lower. What are some situations you do that? Decorative lighting, some things like that, maybe. So we'll. So a good analogy of that. There's a good look at what it looks like. So if you have, that is 20 12-volt batteries in a line, but we need a little bit extra. We need, and we don't want to put a whole nother transformer in there. And we'll look at the money side of that in a minute. Like right here, it says secondary windings of a 240 to a 24 volt transformer. The voltage measurements below. If a 230 volt charger is connected across the entire string of windings, that's the subtractive side. Let's look at the positive side. I got to go back over here. And it would actually drop it. That's the 209. Let me go back over here to this page. Oh. So to put the 20 12-volt batteries in a series in a string, the 240 primary H1 to H4, and the two 12-volt batteries represent 24-volt secondary windings. The voltage measures across the whole thing, and you end up with, as you see on this picture right here, 264 volts at the top. Okay. But on the same token, if you put a battery charger on here, you would only get a portion of that, 230 divided by 22, because it's 22 batteries. That's all the batteries, right? 10.45 volts total. If the load is rated to operate at 208 and connect a string of batteries to 20, you'll have to, it will have close to the rated voltage of 209. 208 to 209 is not a big deal. So. So the question is, why in the world would you even bother to use one of these little transformers like this one on the right over here? I mentioned about the decorative lighting is one respect, and you can use the auto transformer. Y'all keep eating, but I'm gonna mute y'all because you're loud. All right. The complete definition of an auto transformer is in the back of the workbook, and we, by the way, you got a chance to look through, make sure you got Y2 Annex D out. We'll get to that. When used as an isolating transformer, the buck boost can carry a load that is equal to or less than the nameplate rating of the transformer. And why would you do all this? what is the benefit of, why would you just not get a bigger transformer, which that's what Cole would do. He'd get a bigger transformer, right? So instead of getting a bigger transformer, in the case of this thing, we can actually add a little buck boost, or boost transformer, and get 20.8 extra volts for our 208, and we can actually get our 230 on a run where, by the way, where does 208, how do we get 208? Anybody know? How do we end up with 208? It's three phase, right? What has to happen in three phase to get 208? If you go phase to neutral, you get 240, right? You go phase to phase, what do you get? Anybody? Bueller?
Phase to phase, you'd get 208, wouldn't you?
Correct. So in that case, we may still need a 230 volts. That's not good. We need to find that extra 230 volts, and we can do that with that boost by using this little boost transformer, and we get our extra 20.8 volts, and that puts us at 228.8, and that's satisfactory. We can run it in that situation. So, but again, why go through all this trouble to do that? Well, this 240 and 24 volt transformer has a rating of 1 kilovolt amp, or 1 kVA, and the primary winding has a rating of 1.0 kVA at 240 volts, and the secondary winding has it 1.0 kVA at 224 volts. Again, why would you do that instead of just getting another transformer? And we're gonna do the math in just a minute to get the wiring and all that situated. I wanted to show y'all. So in this situation, and we're gonna go back and do the math in just a second while y'all are getting set up over there. This 1 kVA buck boost transformer can supply 9.5 kVA load with a small capacity remaining needed. And so instead of buying a much more expensive 10 kVA, instead of getting a much more expensive 10 kVA isolation transformer, I can get away with that 1 kVA buck boost and that 9.5 kVA transformer. It's cheaper. That's why. That's the whole point of even doing this stuff. All right, so let's look at an example. And this is page, what page are we on? We're on page 224-6 in the book. All right, 208 volt circuit is connected to a 240 24 volt buck boost transformer. The output supplies power to the 230 volt 9.5 kVA load. Determine the minimum rating of the buck boost transformer required for this load. As determined previously, this transformer can deliver 228 volts. We got the 20.8 volts added to the 208 earlier. This voltage is close enough to the 230 volt rating of the load for it to operate satisfactorily. So we got a couple things going on. This is our shutoff right here. So we got our source, 208 volts, right? So we run our 208 volt source, and we can put our little buck boost in here. We can add our little extra 24 volts to it, and we can actually now run our load. So instead of going and putting in a whole nother big transformer inside of the building, I can use this setup. So now you see the amperage coming through, 45.67 amps. Coming out of this one is 4.15. That's the extra we need to get the 45.67, because you got 41.52 on this side, and 4.15 amps here. And that'll give us what we need. We need the 41.52 to get through our load, and everything's good. Okay.
Who supplies the buck booster and where do you mount it?
Where do you mount the buck booster?
Yes.
I would assume near the load. Not
And that's
too far.
something that the owner has to provide, not the power company?
Well, no, whoever's wiring it up is going like if you bid the contract, and let's say you got this load. Let's say you don't have let's say you don't have this. Let's say you don't have this thing yet. Okay. So you're short to run this load, right? So
Yeah.
that's a problem. All right. So they're going to say, all right, you could bid out for say, all right, I'm just going to put a 10 kVA transformer in and I'll fix everything. Right. All right. So
Yeah.
you're going to outbid yourself on the job. You with me?
Yeah.
Instead of outbidding yourself on the job, you say, all right, well, I can just add a boost transformer to the line, and I can now get what I need, and it won't cost as much. And would you be doing it? I mean, right now you guys probably wouldn't be, but if you were the owner of the business, this is one way you could
Save.
Yeah, and you saving money, you probably get a repeat customer too, and it makes more sense than to be inefficient and buy a big old something you don't really need, and it's very expensive to boot. So that would be the point of them. Do y'all use them a lot on the job? My guess is y'all haven't really heard of them.
No.
Yeah, so that tells me, but it could be. Depends on, especially if you're in a big building or something, and you got you just need, like you're on a line somewhere, and you need, golly, if I just had this little bit of extra right here, I could make this work, and that's what the point of this is. Or you could have the reverse. Let's look at that. We'll come back to math. Let's look at the overview of it. Or you could have too much voltage going in. That's a problem too. You agree? So to stop that, we can actually deduct some of the voltage by making it a buck transformer, and we can cut some of it back, and then we've got what we need too. Either way, it's like a little helper to get the voltage right to what you need it to be for that specific load. All right, let's go back. This math is kind of interesting, so let's make sure we get it right. All right, so if you got your book, I'm gonna let y'all look at your book while I'm right here, but I'll zoom in so we can see it on here too. There's our source, 208 volts. This is our buck boost. We've got 240, and we've got 24. Okay. So let's take a look at it. So we got 9,500 VA, right, on our load. That's and we need to know our current for our load. Now, I know it's already displayed right here, but how did they get that is what we're getting at. So we first determined that the amount of current drawn by the load, we know that it's at 228.8 volts. This current will also be the amount of current flowing in the secondary winding. So that's 9,500 VA, 9.5 kVA, or 9,500 VA, and divide that by 220.8 volts, which is what we have. That's with our buck boost. We end up with 41.52 amps. So now we know the current through the secondary. So what about the other currents? Where'd they come from? Where's this 4.15 coming from? Let's find it. So when you take the 41.58, which is the, we know that's the secondary current, and we multiply that by the voltage of this buck boost, secondary buck boost, 20.8, and we divide that by our primary voltage, which was 208, we get 4.15 amps. So now we add those two together. 41.52, that was our amperage going through the secondary. And then we add with our buck boost, we get at 45.67 amps. All right. So for the simple single winding transformer, the secondary and the primary must have a rating of at least. So we need to find the power for the secondary, we need the power of the primary. We need the current of the secondary times the voltage of the secondary. So the current is 41.52 times the 20.8 gives us 863.6 VA, which is close to 1 kVA. That was a lot, wasn't it? Clear as mud.
Very.
All right. So the total output voltage times the rated secondary current, that's what we were getting. So our total output voltage is 228.8. Well, let's see. For the boost example, the total output voltage was 208 plus 20.8. That's 228.8 volts. The rated secondary current for this 1 kVA transformer is 41.667 amps. That's 1 kVA plus, or divided by the 24. And it's boosting at 228.8 volts. That was our overall voltage, and that 41.667 amps divided by 1,000. Because now, let me take this out. Sometimes it's, so before we even get to that, it's 9,533 VA. Okay. The only reason you do, y'all know the only reason you do the divided by 1,000 is to get it to kVA, right? Are y'all good with that?
Yeah, you need it.
Only reason you're doing that is to put the K number back in front of it, kVA. And that's what we read off that number, right?
Can y'all see me?
We don't see you yet, Rex. That could be a good thing.
Yeah, it could be. I'm not real happy right now.
You know what's funny? I've seen you all week long. Every day I've come home, I've come past you coming down the road.
Oh, really?
Yep. I
Poor
honked at you a couple times. Yeah, like you didn't see me, so I just
I probably in that zone coming from the plant.
you know, Cole was just telling us that Jerry's probably gonna start in class next week. We are too.
Where are we, y'all? I'm having some.
We're on page 224, 7. 224-7. We're talking about buck and boost.
Fucking boost.
Can't get here on time. Get here when you can.
Yeah, I learned it from y'all.
Yeah,
15-minute window, right?
there's nothing better than good old McDonald's.
Well, I'm actually having sibling issues here. He says we don't pay on the internet bill, so he disconnected it. I said, well, you don't pay on the power bill, so now what do you think we ought to do, bud? I done lost the internet. I don't have to. I can cut the breakers off in your room. Time to think about it a little while.
And no assault and battery on the video or recording.
I don't work that way.
Don't listen to Mark. Rex, you do what you want, man.
Yeah. So speaking of boosting up, Cole's trying to get you in trouble.
A little X-Lax works miracles sometimes, though.
You're making no crap pies now.
Hey, It's a motivator.
A 240 volt circuit is connected to a 240 32 volt buck boost transformer. The output supplies power to a 208 volt 9.5 kVA load. Determine the minimum rating of the buck boost transformer.
Y'all in the workbook? Oh, man.
Yeah, we're in the workbook 224-7. So if you look at this, this is an example of, you got a 208 volt source, and we actually need it to be 208 running through, but it's 240, so we need to make this part a buck 32 in the secondary, and that's where we get the 240 minus 32 is 208. And it's going to be a little bit weirder numbers when you see it in just a second, but it's not. This one's not as bad to me. That's the one we just did. So we also check it by the windings. So there's 240 turns plus 32 turns is 272 turns. The number of volts dropped across each turn is 240. You got to divide that by that number of turns, but you get a number 0.8. That's up there, ain't it? 0.88253, right? So that primary voltage, H1 to H2, equals the voltage applied to the load. This voltage can now be determined using the voltage of the number of turns in the primary windings, 240, and the volts divided by the volts turn. So 240 turns times 0.88253 gives us 211.76. So now 211.76 and 208. Oh, what you doing there? Why are you doing that? There we go. Stop. So these two numbers, that didn't work out. These two numbers are close enough, right? 3 volts ain't enough to cause a big uproar. So that's good. And that was because at 240 volts, we had those extra turns, 240 plus the 32 turns. We actually ended up with a reduction, a buck transformer. That's a long explanation to it.
Y'all can't see me?
Huh?
Y'all can't see me?
Not yet.
What am I doing wrong here?
I don't know. I just asked to start your video. Let's see what happens. Something's happening. Look at there. There you go. There's
I don't see me.
We'll see you now.
I don't see me.
You don't have to. Well, it's because you see this thing you're looking at right here.
I see it now.
There's a little thing over on your right.
I got it. Yeah, I got it.
The thing you can see everybody. I like it to scroll down the side. I can see Alan's over here picking his nose, and it's all good. All right. So we got our voltage 211.76. That's what we were looking for, and we got that by having that at 32 volt buck transformer. Stop it. Okay. So the voltage is close enough for the 208 rating. What is the voltage across the secondary can also be determined using the same method that was used to find the voltage across the primary. We take the 32 turns, and you multiply that by the 0.88253, and that's 28.24. You add the 211.76 to 28.24, and that's where the 240 volts originated from. And that step is for nothing more than to check yourself. All right. So now let's check the load and see if everything's good. So we take the 9,500 volt amps and divide that by the 211.76 we got back up here, right? Got it right here. All right, and we get 44.86 amps. That lets us know this and the other currents in the buck circuit are shown here. So the total current flowing through the source transformer can also be determined. That's even with the buck, it's still giving us, we still have 240. We still have 240 as the source. That's 9,500 VA divided by 240 volts. That's 39.58. And if you do the buck boost, you take the 39.58 times the 28.24. That's the voltage of the secondary, the buck booster, the buck side, and you divide that by the overall 211.76, and you get 5.28 amps. That's a lot of math. The point of that is to know the buck is where you get the 5.28 amps. That's the added. If you didn't have that extra, this is the amperage you would have. This is the amperage you actually need. That makes sense. This is what you need. This is what you would have if you didn't have this. Yay or nay? All right. The whole point of that thing. That's why you have it. Okay. So again, why? A simple single winding transformer, the secondary and primary must have a rating of at least, it's got 1118 VA, so it needs to at least be a 1.5 kVA. Okay. So this, and long story short, this 1.5 kVA buck boost can supply the 9.5 kVA load, still with capacity remaining. If the 240 to 208 volt isolation transformer were used to supply the correct voltage, the load would dictate that the 9.5 kVA rating would have to be a 10 kVA minimum. Again, this would be a better choice. It'd be cheaper than using that bigger transformer. Saving money, man. Making it work. What's compensation? Transformers with nameplate ratings smaller than 3 kVA are generally designed so that the secondary voltage is slightly higher than the nameplate. No connected load. Typically, with no connected load, the output voltage is 6% higher than the nameplate. So, what does that mean? So if can a 480 volt primary to 120 volt secondary transformer be used to produce 480 volts from a 120 volt circuit? It's called backfeeding. I showed y'all this earlier, or I showed them earlier. That's this is a pad mount right here. This is a pole mount, just like you'd have on your service pole. You got two 120s and a neutral leg. You got 72 or 14.4 or whatever it is running through. It just passes through here. Transformers down at the bottom. On that one, the transformers down at the bottom as well. That one is 7200 going in, and two 120 legs and a neutral going out. So in these instances, backfeeding them would be bad because you would be going 120 to 7200 volts. But in a smaller dose, if you needed something on the job to be 480 and you only had 120 coming in, could you backfeed? And that's what they're talking about here. The transformer connected in reverse, the no load output voltage would actually be about 457. It'd be a little lower. Due to regulation, the output voltage would drop even lower when the load is connected. So you're not going to get that full amount. And there's a lot of other precautions you have to be careful for, because it says it right here. The amount of inrush, the inrush current is the problem. That's like when these backfeed up a line, that inrush is what explodes transformers down the line. So you have to be careful of that. And of course, it's going to open up every overcurrent protection device in America. So you want to comply with the NEC and to avoid nuisance opening. On the primary side of the transformer, when energized, make sure you coordinate it, and you got a centralized overcurrent protection device for that. Usually an engineer takes care of that. You ain't got to worry about that stuff. Transformers that are backfed can exhibit particularly high inrush currents. That's a nice way of putting it. Yeah, there's a lot of voltage can come in, and that's why I say caution should be exercised. Very dangerous thing to be doing. Very dangerous. I mentioned the crane safety video. I'm actually going to scroll down here, kick back to the lesson here. And it's right here up under our meeting today. That was our meeting Zoom. But right up under that is our rigging and safety video. I'm gonna let you watch it.
If my man was wearing this, I would be all over him.
Yeah, that's weird. But anyhow, it's on there, and it just talks about it. It shows one thing for it shows the guy actually getting electrocuted. It's not an actual person though; it's a reenactment. So just to be very careful where you put a crane. Death can be imminent if it touches a line. There's one, I looked up a video, and you're more than welcome. Y'all do Google searches all day, so it's no big deal. There's one where a guy, he put it next to
Keep on, or I can mute you. What do you want to do?
who do what?
I'm having sibling issues here.
Yeah, I'm gonna mute you. All right. So anyhow, the crane got close to a 115 kV volt line. It was within 3 or 4 feet, and arc jumped over to it. That was bad. Caught the machine on fire. Look that one up. That's pretty cool. All right, flashcards. What's an isolation transformer? Now y'all can turn y'all's on. Here we go. Unmute them. So this one is the one, has a complete electrical separation between the primary input and the secondary. And that's a buck boost can be one, but it's one you put separate from whatever you're going to put whatever the load is. But you bring it in, and then boom, this transformer helps. It could be that, like I said, it could be a all-in-one, or it could be one with a buck boost on it. All right. What about an insulating transformer? I can see y'all still got to go back and do the other lesson. A transformer is complete electrical separation between primary and secondary. All right, polarity. By the way, there's a video on this. It was pretty terrible. What is polarity?
It's like with the magnetic field and shit.
Close.
I mean, I didn't mean to curse. I forgot you were recording this.
Yeah, we'll send you to Atlanta. It's no big deal. No, magnetic field, but more in particular deals with
Which way, like positive and negative for?
Right. We have a north pole and a south pole. Those poles are negative and positive, right? And it's the voltage obtained by the primary winding in relation to that and the secondary winding. All right. So
These are very specific.
huh?
And these are very specific.
Yes, it said that's so compensation. We talk about compensation at work, right? We want to be compensated for the job. But more than that, it's dealing with the correction of the high transformer regulation voltage drop under load, and by adding a few additional turns on the secondary. Okay. Let me go here. Then that auto transformer, buck boost can actually be used to turn into an auto transformer, and it can be electrically connected. So it's a good Good deal. All right, I think we got all of them. Yep. Cool. And those are on your thing. You can pull them out. All right. All right, let's see how much y'all can do here. All right, this is the sum of the voltage across the higher voltage winding to the lower voltage winding. All right, so let me help you with the word there, sum. What does sum mean in math? S-U-M.
It's add.
That's right, we're adding something, right? It's the sum of the voltage across the, so is it additive voltage waveform or
B.
additive voltage measurement?
B.
Okay, very good. So this changes or transforms only a portion of the electrical energy it transmits.
Isolated? No, I mean, step down.
No, it changes.
I was going
transforms
isolating.
only a portion. So it's either this one or,
Auto.
so the isolating is what's cut between, it's between the primary, it's separate between the primary and the secondary. That makes sense. The auto transformer, it can actually only, it'll only change as a portion. That's why we use that. That's why we use the buck boost. Correction of the secondary voltage by adding a few additional terms.
Compensation.
Compensation. We all want to be compensated. That's right. So even a transformer. Okay. So when buck boost transformers are connected to buck the input voltage, the primary and secondary voltages are. Let me help you.
Additive.
Y'all see that? Y'all can't see that. Hold on. Let me stop the share a second.
Subtractive.
Correct. Buck is subtractive, boost is additive. So the answer is subtractive. Okay. Buck means subtractive, boost means additive. All right. And we hadn't done all the crane stuff, which we're going to get into it in a minute. They're often used for high rise, urban areas, small footprint.
Tower.
Yeah.
I thought it was locomotive.
You know, you laugh, but out at Vogel, there was a locomotive crane.
Big Blue.
Big Blue was it 2 locomotives ran it?
I don't know. I just thought it came in on a train and it stayed on a circular train track.
They actually had to build the train track and they lifted it onto the track.
They anchored it down at the center point. I forget how deep they went. It was like a crazy number.
Yeah, it's a friggin', it was amazing crane. And they built another one in South Carolina and then they just tore it down. I don't know where it went, but I don't even use it anymore. So sad.
Didn't one of those football stadiums get knocked down by a Big Blue crane? Or they called it Big Blue?
Not one like the ones they use at Vogel. Those were the 2 largest. The one at Vogel and the one at VC Sumner was the 2 biggest in this side of Mississippi. They were massive. They put a flag on top of ours to say it was taller. All right. Let's get to our fun stuff, which is the reading worksheet. So speaking of buck boost, we're going to have some calculations next week. This week is about basically getting the how they work. All right, polarity is a term associated with what kind?
Single phase.
Single phase transformers. Okay. We're on the reading worksheet. All right, Alan, I'm gonna put you on the spot. Small transformers, less than 3 kVA, have high transformer regulation. Voltage regulation means,
I don't have my book in front of me, so.
he doesn't have his book. All right, so you know what I need to do? I need to give Alan a demerit. I'm gonna help you out, Alan. I'm a nice guy. Sometimes. Here we go. Let's help Alan.
Thought I was giving him a pretty good hint.
Let's start the quiz now. Single phase. Here you go. You see that one? Where'd Alan go? He ran away.
He ran away. It's A.
Come back, Alan. Come back. All right, so what do y'all think?
It do be A.
The output voltage drops and the load is connected. That is in reading assignment 224.3 if you're looking for it. 224.3. All right, Cole. Buck boost transformers are available with secondary windings that are rated to deliver voltages of.
Any of these.
Correct. Sure, they can do any of those. 48,
Well-
16, 12, 24, 32.
What worksheet are we on again?
Who did what?
224.
Okay, because my questions weren't lining up. Hold on, give me a second.
Are these the same questions? Ain't they?
I think I was just,
Yeah.
Okay.
We're on 224 reading worksheet. And that is under the reading assignment for 224.2, by the way, if you're looking for it. So for transformers, here you go, Rex. For transformers smaller than 3 kVA with no load connected to the output leads, output voltage can be expected to be about, and this deals with compensation, so. Oh, we lost you, sound-wise.
Got me?
What'd you think?
I'm gonna say D.
No, 6%.
No,
That's the compensation rate
okay,
for transformers. Okay,
thank you.
all right. When a supply voltage is to be changed from 120 volt to 24 volt, a buck boost transformer is connected to what part to deliver the proper voltage to a 24 volt load?
A.
Insulating transformer. That is correct, sir. Where circuit voltage is 208, a buck boost transformer can be used to operate a load that is rated to operate 240. True or false?
True.
That is true. That's the whole point of the buck boost, right? All right. Which of the drawings shown, this figure is connected to an auto transformer. So let's look at them. A phase, B phase, B phase, C phase. 208. Which ones? I think. Is it both? 1, 2?
I picked 2 the first time and I got it wrong, so I'm gonna go and say it's a 1 only.
So, because we had it is run, yeah, and this is the way it's run correctly right here. You get the 208, which is what you were after. It is 1 only. 2 would be just a transformer because you're getting out what you needed. Okay. Which of the following is connected to an isolation transformer?
2 only?
That is under reading, or actually, so go to this go to this right here. So look at Y2 Annex D. And there's some diagrams. And it's
You talking about the diagram K, L, M, and N?
so there's a diagram that shows you connection diagrams. Okay. These are all auto transformer connection diagrams. All right. Just for your record, so y'all know. And we also have three-phase, which we'll get to later. But single-phase auto transformer diagram. Okay. And yes, the answer is 2 only. Okay. Smaller transformers, typically 50 kVA or smaller, operating at 600 volts and below the normally wound, are normally wound for what?
Additive.
They're normally wound for additive, normally. Larger capacity or higher than 600 volt transformer are typically wound for
Subtractive?
right.
Subtractive.
Normally it's going a lower amount. See if we got 100. Maybe, maybe not. Oh, we're smart. All right, y'all good with that?
Fantastic.
Okay. All right, let's look at the crane stuff. But this thing here, when you're doing 224.2 and 1, 2, and 3, you need this. Okay, you need this. Make sure
Is that the Y2?
Y2 Annex D, not
Okay.
Y2K. Y2 Annex D. Okay. Hang on just a minute. I'll get the crane stuff. This right here. If I mess around, I don't put this back in here, and I will lose it. That will be bad. Bad.
Hey, so the video you were talking about the crane,
Mhm.
is it 2 shocked after crane hits power line in Lantana?
2 shot. Well, here. It won't take but a second. We'll just watch this stupid thing. It's very short. It doesn't take long at all. Luckily, it's not the real person dying, so it's not too bad. Here we go. 1, 2.
If my man was wearing this, I would be all over him.
Yeah. Commercials.
That smells really good.
Here we go. Crane hat.
I think you muted it.
Crane boom from a storage area to another area of the shipyard. The riggers were positioned at both ends of the structural sections while they were being transported. After the first section was delivered, the men noticed their original route taken to deliver the first section was now blocked by another working.
Now, I know none of y'all would ever, just in the sake of time, say, screw it, let's just go another way. Y'all would never do that, right? Yeah,
Hell no.
yeah, you would.
Wait for them to move.
That's why, yeah, that's what you should have done.
Crane. Rather than wait for the crane to finish and move out of the way, they decided to take another route to the work site.
They were in a
As
hurry,
they
they ready to get
transported
home.
The second section, the 2 riggers focused their attention on keeping the load headed straight down the narrow path. All 3 workers failed to see the overhead power lines. The crane boom contacted these high voltage power lines. 7,200 volts passed from the power lines through the wire rope into the suspended structural section to the rigger, who was still holding on to the section. The rigger was killed instantly. Let's look at some of the contributing factors that led to this fatality. En route to their work area, the crane traveling with the suspended load struck overhead power lines. A safe route was not established before the crane was moved. A designated person must establish a safe traveling route for cranes. Equipment must not be operated or positioned within 10 feet of an energized power line. The rigger holding onto the load provided an electrical path to ground. Always use.
Now I'm going to go on and tell you that most farming equipment and people do not pay attention to this. A lot of folks, period, don't pay attention to this like they should, because you use this big equipment, bad things tend to happen.
Use non-conductive tag lines to control loads. When practicable, tag lines should be clean and dry. Riggers assigned to assisting the movement of the crane and load must ensure sufficient distance is maintained between the extended boom of the crane and power lines. Ensure riggers are adequately trained to recognize crane hazards. It is recommended that power lines be clearly marked and visible, as well as other overhead hazards. If workplace conditions change, another hazard assessment should be performed to determine whether previously unidentified hazards exist. Although not contributing to the fatality, it is recommended that loads be carried no higher than necessary, normally waist high, to prevent contact with any other obstruction.
Well, they got a whole other problem with this is, crushing on them. It could fall on them. There's several other where and in your book it shows hand signals or a crane operator. This is the same folks, or not the same people, but the same people who put this video out. The crane was moving back and forth. Happens a lot with excavators too. Somebody's not paying attention and get too close to the back of the excavator. The guy swings around and squishes them. He didn't, most of the time the excavator or the boom guy has no idea he killed somebody because they don't feel it. So you're just like a bug on a windshield. Gross, but it happens. So be careful when you're around a crane, because especially you guys on the job site. Lucky for y'all, most of the time y'all don't have to get around them, but every once in a while you may, and you want to make sure that you keep yourself safe.
You hear that whistle blowing, you better look up.
Well, most of them are supposed to have some kind of noise device, or a lot of them, they have horns or whatever, and they'll blow the little horn.
Yeah.
But that's not always the case. And you hope they do, but as well as I do, there's some job sites that are a little sketchy. So when you should make sure you're on high alert when you're on those job sites, because some people don't pay attention. All right. You should not touch or lean against a crane at any time.
True.
That's the other video. If you look up those videos, the other video, that's what the guy did. He actually leaned up against it. He was talking to his foreman, and when the foreman walked away and the other guy walked away, he stayed right there beside the crane, not thinking about, I guess, because the guy's probably chewing him out or whatever. And when the guy turned back around, he squished him between the outrigger and the crane itself. When in operation, the crane must be kept a minimum distance of how far from the power lines that are 50 kV or less?
10 feet.
10 feet. That's correct. There are only 2 types of cranes.
False.
Yeah, there's many types of cranes. When signaling a crane, any hand signals can be used as long as all the employees agree on the method.
Sounds good to me.
It sounds good, but if you look over here, these are some commonly used hand signals, and they got to fit the OSHA.
I lost y'all. What'd I do?
You're still there?
I don't see y'all though.
Or you probably minimized it.
I
Yeah.
see you, bud.
Just
I'm
hold tight. We're almost there.
We're looking right into your home.
We can see you, buddy. See the bird dog on the wall by there.
That's Ralph.
All right, so by the way, it's false on the hand signals. They have to be they need to be
OSHA approved.
OSHA approved. Something that is pretty standard. Because if you go on another job site and they may be using a different type of signal, well, you can see what bad could happen there. Never stand or walk under any loaded suspended by a crane. That should be
True.
sense. Yeah, but you'd be amazed. There's not a lot of that going around. True. Cranes are used to lift and place.
1 and 3 only.
Yeah, we don't lift people, even though I know you've seen people on forklifts using it as an elevator, but it's not safe.
I thought they had a basket made for that.
Yeah, I was gonna say I did that the other day in an actual basket for a forklift, but
If there's yeah, it's got to have all the right stuff, but normally they're not made for that. Cranes, as with all other types of equipment, can be operated only by
qualified.
well, qualified is good for electrical, but in crane world, you can do qualified and trained. How about that? So it's E. Most common types of crane accidents involve getting caught in moving structures and
Electrical lines.
electrical lines. And there's one other problem they have, not cave-ins, but tip overs.
We had one do that at the plant.
Yeah, y'all had that happen a couple of times, haven't you?
I just saw one since I've been there.
I think y'all took some pictures and showed me. That was like our first or second week of class, wasn't it? When that one tipped over.
I think they hire people to actually do that, teach the others what not to do. I mean, really, come on, if you train, you should know not to tip one over.
Yeah, you would think. You would think. Oh, that's
Trying to beat a train at the railroad crossing.
all right. So make sure that you are caught up before next week's class. We will meet in person.
I'll try to do better.
I'm going to send out nasty little reminders this week. Julie's been telling me to send out nasty reminders. I'm going to do such.